Hello. So let's start. Now, before we start, these slides are already available online, so there's going to be a few links in there, so don't worry about trying to jot them down or anything, because they're already online. So Android, like nearly every other kind of UI framework out there, is single-threaded. So it has one thread which you do all of your work on. So things like view inflation, that's the bulk of the work which happens actually. As in, like, big chunks of work is view inflation. That takes, it can take hundreds of milliseconds when you're on create, it's called. Also, measure and layout, that's the thing that continually happens as you update your UI. And they're actually they're small chunks of work, but they happen repeatedly, and actually they mount up, basically. And then drawing, not so much drawing happens on the main thread these days. We have things like render thread for animations, but there's still quite a lot of sort of vsync which happens on the main thread. And then there's a load of other stuff, which includes all of your code, like all the entry points into your activity, on create, on resume, and then all the stuff you actually run. The entry points are on the main thread. Now, the vast majority of devices out there are 60 Hertz. They have a refresh rate of 60 Hertz, which gives you roughly about 16 milliseconds to update the UI and so that you don't have janks. But you can imagine that there are devices out there which have 90 Hertz, and the Razer phone last year, the 2017 Razer phone, had a 90 Hertz display, and that gives you only 12 milliseconds to do the exact same amount of work. And actually, the Razer phone this year, I think, has a 120 Hertz display. So it's exactly the same amount of work, just you've got half the time to do it. And if you look at systrace, you'll see that so systrace is a debug tool, allows you to see exactly what's happening on the CPU, on the GPU, and all that stuff. Allows you to really drill down into what's actually happening on your device. But we've kind of fixed a lot of this system stuff now. So a lot of the things that push apps over the edge of like vsync, vframes, is app code. And I don't mean it's all your fault, but it's stuff that apps are doing. Like inflation, that takes a large amount of time. It's just what it is. And so how can we actually fix that? And the way you kind of do it is we want to make stuff async. Most phones in your pocket have at least kind of 4, maybe 8 CPUs in them. So we should use them as much as possible, spread the workload across all those CPUs and get as much bang for our buck. So how do we do that? So in the past, we gave you tools such as AsyncTask, which came out in sort of API free, so that's Cupcake, if anyone was back around then. But unfortunately, it has a lot of issues, especially around rotation, which is a lot of the reasons why we have things like vModel now. So we don't really want to use AsyncTask. I think it's even deprecated now. Then we have Executors. Now, Executors are a Java thing, and they allow you to kind of group together threads into a nice sane way so you can execute code. Now, Executors, threads themselves, when you create a thread, actually takes about 1 megabyte of RAM for each thread running on your device. And so we don't want to create threads willy-nilly. So Executors are really nice because they allow you to cache them together. So it can cache threads internally, but the actual API to use this stuff is pretty simple. You have an execute and you give it a runnable. There's no kind of switching threads. There's no way to come back to different threads easily. All that kind of stuff. It's just not very nice. Loaders were nice in that they were added tightly into fragments. And so they allow you to kind of have that flow where you do something in the background and then you update the UI. The problem is that the implementation we only gave you only really worked with content providers, which no one likes. We know that API is horrible. And so, yeah, they're even deprecated now, I think. Or at least the old ones are. And so as you move, like if you think like Java stuff, like features, and so features are actually really nice, like as a concept. Place services have started moving to their own little future-y type class. But for developers to actually use them themselves, unless you want to import all of Guava, which no one wants to do because it's megabytes in your APK, and unless you have a MinSDK 24, so you can use a completable feature, again, it's not an option. And then we have libraries, so RoboSpice, like one from years and years ago. Volley, which was something we kind of produced and then never actually shipped to you. We only give you source code, which is really stupid. And then sort of the ever popular RxJava now, the latest kind of poster child of doing things on the background thread. And so this kind of leads me on to sort of the new thing, which is coroutines. So hopefully if you're sat in this talk, you don't want to know how do we do that, you want to know why we do that. So why do you actually use coroutines? So what does your typical app do? Now, for the most part, I'd say most apps are CRUD. And I don't mean the slang word in American. I mean the fact that they create, they read, they update, and they delete data. When you think about it, it's all about data input, really. Think of Airbnb, it's all about listings. You know, you modify a listing, you create a listing, whatever it'll be. And then most apps will also have sort of a sync component to it. So it syncs up to web services, it comes back down. So in fact, most apps are actually pretty simple, like at least computationally. There's not a lot that actually happens on the CPU as such, as in like it doesn't really push and peg the CPU like a game would. Yes, the logic can be kind of tricky, but in terms of actually what your device is doing, it's not actually that hard really. And now, of course, we as a platform and Android put a lot of stuff in your way to actually get things right. You know, UI frameworks, UI redesigns, material, blah, blah, blah. And so we obviously make your jobs harder. But in terms of the actual apps, they're kind of pretty simple. So why coroutines? So I think they're great for your I/O tasks, especially on a resource-constrained system like mobile devices that we all write for. And they definitely scale on limited hardware. As I said earlier, like each thread that runs on your device is about 1 megabyte to 2, it depends. And each coroutine is it's just Java object on the heap, so you're looking 10K, probably less than that. So it's a whole lot less RAM usage. And the more important thing in my mind anyway is that it's a much easier development model. So instead of things like Rx, we have like chains of, 20 things of operators. It's imperative code. So it's just line after line that you're reading. It's a lot easier, especially for someone coming into the platform or it's like a new developer, new in your team. It's a lot easier to actually read that code than sort of an Rx chain, in my mind anyway. So all the stuff I'm going to be talking about is an app which I've been writing for the past sort of 12 months or so called TV. You can find it there, it's all open source. But yeah, it used a lot of Rx and I've slowly been moving more and more towards coroutines. So as kind of mobile developers, one of the big things we have to think about is disk space, APK size and download size at the same time as well. Like emerging markets, they have, the connectivity is less and also disk space. Like they might only have their devices might only have like 16 gigabytes of storage or whatever. So we need to make those devices, your APKs as small as possible really. So when I was thinking about this, it's something we all care about with libraries. Bringing in more dependencies basically equals more strain on your APK. And so in coroutines, there's kind of 3 libraries that you're probably using. Core, which contains the majority of what you're going to be using. Android, which is it brings in kind of support for the Android main thread. And then RxJava. RxJava is like a kind of extension library, which allows you to interop between RxJava and coroutines. You don't have to use that if you're not using RxJava, but I do. So for this example, we're using the 3 libraries, and if you look at the jar files, you just download them off Melbourne Central. It's about 774 kilobytes, which is quite a lot, actually. But as soon as you actually put them into your APK, it comes down to about 500 kilobytes. So actually, when they're packed together, it's not too bad. And again, for Android developers, we need to think about method references, especially if you're targeting before Lollipop. We don't have multi-dex there, so we need to make sure that our method references are below 64K. But as soon as you start turning on R8 or ProGuard, whatever the minify is of your choice, that actually comes down quite heavily, down to about 113K. So we've chopped off, less than a quarter, more than a quarter, off it. And including the method references, they've come down drastically. And if you turn on optimization with ProGuard or R8, that comes down even further. So we're at that magic point where we're below 100 kilobytes. So it's not really that much of an issue anymore. The important thing to know is that there's a ProGuard rule you need to make sure you insert. This is just taken straight off the Coroutine doc. We don't currently have a way of shipping that in the jar files, so you have to make sure you do it yourself, but whatever. So hopefully by now you're kind of thinking about using coroutines in your app, or at least you're kind of interested in it. So let's actually look at how you actually write them. So here we have a method, which is a method taken from my app, which you're given a show ID and it does an update. And so first it will grab the current show from the database, the local store, and if it's in there, and then it will get it from a remote source, whatever that remote source is, and then it will get it from another remote source. It will kind of do some merging. And then it will merge all the results together and save it. It's a pretty simple kind of flow, which most apps will have. But you can kind of see that those 3 tasks there are all kind of interdependent. So they're all just have one input, which is the ID, it's a long, and then they all run sequentially. We don't need to do that. We can have them all running concurrently. There's no dependencies in between those tasks. So how do we do that? Well, Coroutine is really simple. We have the async builder, which is very similar to sort of async and promises and JS and even C#, which is kind of where it's kind of come from. And then, so we'll go for it. So our first one from our local. So again, it's just grabbing it from the show store, but because we wrapped it in an async, we get this, what we call a deferred back. And that's kind of like a promise. And again, for the remotes, we'll do the same thing. We'll wrap into asyncs. And now these are all 3 independent tasks, which are all going to run kind of concurrently. And then finally, when we get to this bit, we actually want to listen, not listen, wait for the result of each of those in turn. So once we've got the actual result back from each of those tasks, we can merge them and save them. So that's as pretty simple as it gets with coroutines. Like, it's actually really pretty simple. You can imagine that with Rx, it'll be quite a lot of chains. So yeah. And that actually looks imperative as well. Like, it's line by line. I think anyway, it's a lot easier to understand. So async is when you actually want to run something and then kind of await the result, which is kind of most of the tasks you want to do. But what about when you just want to fire something and just let it run and it does its thing, which is kind of what threads kind of do. So we also have another builder for that as well. So here we have a button, which when it's clicked, it will do something. And for that builder, we have something called launch, which is kind of a great name. And in this particular example, we could fetch something from the network, and then we'll kind of do some UI stuff. It doesn't matter what that does really, but the fact that all of the code in that task does all it needs. Like, it's not waiting for a result, it doesn't come back, it just does all it needs. And so yeah, launch is for when you just want to fire and forget. That's exactly what it's for. You fire a task and you just let it run to completion. So that's a little bit about sort of background of coroutines. I haven't gone too deep on it because you only really need to kind of launch and async stuff for now anyway. So how do you actually use them on Android? That's the more important thing here. So the simple example is kind of this. So here we have a view model, which is kind of the architecture components from the architecture components, which we released 2 years ago, whatever it was. So the first bit of the code is just kind of internal state. We have a repository which kind of holds all our logic, and then some kind of state. And then we'll in our init, which is kind of the constructor. So when that view model is created, we'll have a refresh method. So every time that view model is created, we'll do a refresh, which kind of feels like what you want to do. In that refresh, we'll launch something. We'll launch a refresh task. And that just calls a method called showRepository.updateShow. That's pretty much as simple as it gets. But can anyone see the issue here? What happens if the view model actually gets cleared? So it actually goes away before that task has finished. You're going to get, number one, wasted work, and number two, if it comes back, it might do something a bit weird. We need a way to actually cancel it, basically. And that's where jobs come in. Jobs is the way that you get assigned a callback and you can actually cancel them later. So we go back to our example. Launch itself actually returns a job. And so yeah, you can actually keep hold of that reference. And so later on that job object, we can actually call .cancel. So that's the cancel method. So we wouldn't actually do that here. Like, we wouldn't just launch straight away and then cancel. It's just an example of what the method is. We'd actually do it in onCleared. Yes, that's so. And so what you'd actually probably do is you probably keep references to each job that you want to do. So you might have actually more than one job run at a time. So you'd keep a variable at the top, you'd keep reference to that job object, and then later you'd actually call onClear. In onClear, you'd call cancel. But the problem is that you probably have more than one task run at a time. You won't just have one, you'll probably have 3 or 4 or whatever it is. And so if you have another one, you can have another job at the top and then another clear at the bottom, and then you have a third, and so on and so on. RxJava kind of gives you a nice way of doing that called composite disposable. So it's more of a kind of collection. Coroutines goes a different way in that we have like kind of a parent and child relationship instead. So really what you want to do is you want to scope, if you think mentally what you want to try and do here, you want to scope the coroutine, the lifecycle of that coroutine, to the lifecycle of something else. In this instance, it's a view model, but it could be a fragment or activity or whatever it is. And it brings on to the subject of scopes. So this is something kind of new in coroutines. Previously, we had this kind of manual way of doing it. But we now have a new way, what is being deemed as called structured concurrency. And it's a whole kind of topic which goes far deeper than kind of this talk. So if you're interested, go and read it. There's lots of docs online. But for the interest of this talk, the thing we care about is something called Coroutine scope. And it allows objects to provide scope for coroutines. So you can imagine that object could be anything that has a lifecycle. In our lives, it's going to be kind of view models or fragments or services or whatever it would be. For the async and launch actually become instance methods on the objects, basically, instead now. Previously, they were like static methods that you can call from anywhere, whereas now they actually become instant methods. And so launching and building a coroutine changes from, I just want to launch something, to I want to launch something on my activity. So it kind of changes that mental model. It scopes something to something else. One of the things you have to do when you use coroutine scope is an interface, is that you have to provide a default context. And that context tells the coroutine how it's going to be run. So let's go for an example. So here's a very simple example. So we have our view model, and the first thing we need to do is implement the interface. If you actually look at the interface, it's very simple. It only has really one thing, which is it forces you to create a coroutine context. And as I said earlier, that's the thing that tells the coroutine how it wants to be run. It's kind of like an Android context. It contains all the information that the coroutine needs to be able to run itself. In our kind of what we want to do here, we want to give it a job. So we want to have a way to call back and cancel it later. And also, we need a way to tell it what it needs to run on. That is called a dispatcher, but we'll talk more about later. But for just as a quick example, a quick explanation, all coroutines here will run on the Android main thread. That's what it says. So our launch looks exactly the same. So we're just using the launch method. It's actually changed slightly internally because we are inheriting that coroutine scope interface. What it actually means is this instead. So it kind of means this dot launch, and then you kind of implying the context to be whatever is provided by the coroutine scope. It's actually a bit more complex than that internally, but there's more layers as all libraries have, but that's pretty much what happens. So you can actually abstract all of that away quite nicely into a base class. I wouldn't expect anyone to write this. We're actually currently trying to think of adding this into the view model classes, so you wouldn't actually have to think about this. But it's a very simple implementation for a view model. You can just copy and paste that and extend it. So we actually think and try and I was trying to think of how to visualize coroutines, and this is the best I came up with, so bear with me. So here we have our launch, and if you remember back, all we did was call in one method, which was called update show. So let's look at how it actually runs. So at this point, our launch is running. So our coroutine is running, which is denoted by that blue thing going around. And we're in the first line of that first method, update show. All right, we've passed the first call to async, and that is loading. And so that loading coroutine is loading. So it's running in the background, it's going to the database, it's doing some fetching or something, or whatever it was. But yeah, that's running. And then we go past the second entry point, which is the second async. And again, that second coroutine is running. These are now child coroutines. So that outer blue one is the main one, and then the two inner ones are, well, children. Now, as soon as we pass those 2 points, because they're non-blocking calls, which means they just pass straight away. And so we get to that first await. So at this point, we're awaiting that first coroutine to actually finish. And it hasn't, it's still running, so we're still sat there. And what that means is that the outer coroutine, the big blue one, is what we call suspended now. It's just sat there waiting for another coroutine to actually finish. But in this example, our view model has been cleared while this has happened, and we've been cancelled. The coroutine's been cancelled, and we're just sat there now. Now at this point, you can see that those two inner coroutines have actually cancelled at the same time. That is because of the implicit functionality that scoping gives you. So it's not just about the fact that a fragment can control the control lifecycle of a coroutine. Coroutines can control inner coroutines at the same time. So that scoping works all the way down. So it's kind of cool. And yeah, those two children are cancelled too. So hopefully you can see kind of the benefits of the scoping, the way it's kind of forcing you to go down. and it's got the implicit functionality that it's been provided. Now, I've spoken a lot there about view models. I'm sure a lot of you aren't using view models, or at least you have your own kind of classes which are view model-esque. So you can do something very similar with Fragment. As the implementation we have of view model earlier is an implementation for Fragment. It's exactly the same, other than the base class has changed really, and the callback's slightly different. Again, it's super simple. Last year, we also provided a way where you can observe lifecycle as well as kind of like trying to override methods. So it's much nicer. It's composition over inheritance, and it's much nicer to actually do. So as a quick example, we have a thing called a lifecycle observer, and you can kind of override in the methods on that. The two here on create and on destroy, and then to use them, you just call getLifecycle.addObserver. It's the observer pattern. And so wouldn't it be nice if we can do that with a scope as well? So let's build it. So we'll create a class called lifecycle scope, and it will extend the class lifecycle observer. We only really care about onDestroy because we just want to know when to cancel that job. So we'll override onDestroy, we'll create a job, and then we'll call job.cancel. And then we need to, again, implement the interface and create the coroutine context. Hopefully you've just seen like 4 implementations of the same thing there. But yeah, as I said, it's really simple to actually write these. And that is your lifecycle scope, basically. And to actually use it, so here we're using it in a fragment. You could do it other ways with a fragment, but it's an example. So you just create an instance of it, you add it as an observer to the lifecycle, and then you can do scope.launch. And then whenever that launch is called, it scopes the lifecycle of the fragment. Now you can actually create lifecycles for whatever kind of component you want. It could be a custom component, I don't know. It doesn't have to be a fragment. It's actually a quite extensible API that we have. So if you have something, I don't know, some kind of weird widget, and you want to expose your own lifecycle, it would also work with that. And yeah, it's now scoped to the fragment lifecycle. Now that's a really simple example, which doesn't actually, there's quite a few caveats to it. Louis, who's a prominent Kotlin developer, has written a really nice implementation, which you can find here, if you actually want to just drag it down instead. So I've spoken a lot there about cancel, the cancel method on job, and that brings on to the subject of cancellation. So cancellation on coroutines requires cooperation. It's kind of like thread interrupts in a way, but it's much less explicit. And explicitly, you need to check, when you're running the coroutine, you need to check if you've been cancelled. Or more specifically for the API, you need to check if you're still active. So you're given like a state which is active or not. There are 2 ways to cooperate. The first is by just simply calling a suspended function. Whenever you call one of those functions, the example they always give is yield. That will automatically do basically a cancel check, and if it finds that you are cancelled, it will just throw an exception, and that will bubble up, and that's how it internally populates up. So that's the easiest way. Just call yield occasionally, and it will just work. Or you can actually do it manually. We also give you as a property called isActive, which you can check yourself. So in this example, we're just going through some files, and we're going to do some long running on each of them. So a quick way of doing that is just doing if check on isActive. So we just spoke a little about exceptions. So 2 things which have kind of caught me with coroutines and exceptions lately anyway, well, especially when I was starting out, is that they handle slightly differently. So the first is that launch actually rethrows exceptions. So it kind of works a bit like a thread, in that any exceptions which happen while they've been running will get sent to the default thread exception handler. So here we'll go back to our update show and say we throw an exception at the end. At that point, what will actually happen is that it's treated like an uncaught exception, which means that basically your app crashes. That's pretty much what, which is kind of what you want. You can catch it easy and like actually work out what's changed. Async is slightly different. So because async is all about you trying to run something and then you trying to handle the result later when you call await. It will actually not throw the exception while it's being run. Async only throws the exception when you call await. Which is kind of bad. Well, it's not bad, but it's kind of you can kind of misuse it in a way. And if you forget to call await, which is not that hard to do, you can just swallow exceptions and you'll never know it's happened. So yeah, as an example again, so instead of throwing down at the bottom, we now throw in an async block, whatever. But the actual exception isn't thrown until we get back down to here and it waits. And so yeah, if you accidentally use async instead of launch for like a fire and forget thing, that can easily allow you to get into swallowing exceptions. An easy way to fix that is just easy try catch, which is this. It's the standard way of doing it. So we spoke a little bit earlier about dispatchers and how coroutines run. So we should talk a little bit about how they actually run on your device. And that's where dispatchers come in. So here we have a launch, and by default, internally, there's a default parameter value called context, and that defaults to using what we call the default dispatcher. So what's a coroutine dispatcher? It's the thing which schedules and runs your coroutines. On Java or JVM language, it actually runs on threads internally. Dispatchers.default internally in the implementation is called default scheduler. You don't really need to know the name, but you should really know how it works internally, which is that it uses a parallelism, which is a very hard word to say, of a CPU count. So it's not great for I/O stuff, because, I don't know, on your device, you might only have a thread pool of 4. So if you're downloading a load of images, it's probably not going to work great. But it is an elastic thread executor, which we'll talk about in a bit. And it's now the default too. A new one came out in 0.25, which is about 3 weeks ago. And it's designed explicitly for I/O tasks. And that's because it has a parallelism of 64 minimum, which is great for things like network requests, loading images from disk, whatever it would be. Because you're probably bound to have more than sort of CPU count running. The great thing about the I/O and the default scheduler is that they actually share thread pools internally. So it doesn't sound that great, but when you have things like this, so we have an async, which is being run on that default dispatcher, and then we're going to switch to the I/O dispatcher to do some disk stuff, and then we'll do some processing after. Now, they're actually 2 different dispatchers, and so if they weren't using shared threads, you'd have to do a thread switch, and that takes time and memory. Whereas because they're using the same thread pool, it actually just internally does like a different allocation internally. It all just runs on the same thread. So it's actually kind of cool. Oh, yeah, I'll step through it. And so taking a bit of a segue into sort of reactivity now. And so how many recent blog posts can kind of be summarized as this animation? And myself, I've also been guilty of this. Now, I'm going to make a kind of assertion here, and that most devs use RxJava just because it makes threading really easy. Of course, there's still devs out there who kind of like live observable and everything's observable. But I think a lot of them end up just mainly using single, maybe incompletable. And the fact that you can use that and then do schedule on to switch the threads really nicely, it's kind of 19% of use cases maybe. The problem with that is that actually single, maybe incompletable, actually only live in RxJava, RxScala, and RxGroovy, which maybe is a reflection of those platforms rather than the fact they're needed in Rx. So I don't know, that's something I thought. So I'd say that coroutines can quite easily replace your single, maybe incompletable calls, because they kind of do mentally anyway the same thing. You're getting one thing from a network or whatever it is, and you want the result back. And it has the inbuilt support to actually switch threads internally. And so yeah, I kind of think the same thing. So if you go for a small example, as a retrofit kind of interface, and you can see that return type is a single. And to use that, it's an Rx chain. That could be a lot more complex. I'm sure there are many more complex ones than that, but it calls 2 methods at the end, unloaded and on error. But you can actually consume Rx observables or single or whatever it is really nicely with coroutines. So as I said earlier, we have that coroutines extension library. So instead of having to do all that chaining, you can actually just call await, which is an extension function provided by that library. And it will basically treat that Rx subject, or whatever it is, observable publisher, as a kind of awaitable, as an async. And so you can actually, it's really nice in that if you're slowly moving towards coroutines, you can kind of bridge and kind of like slowly move over using these extension functions. But wouldn't it be nice if we can just make that retrofit call a suspending function? Get rid of RxJava altogether. And yeah, we can. It's actually coming to get retrofit pretty soon. I was talking to Jake about it a couple weeks ago, and he said it's already implemented. It just needs to be released. So yeah, I think he was waiting for Coroutines 1.0 to come out, which is happening imminently. And then yeah, our consuming code comes from that to just that. It's just a suspended function which you can call anytime. So that kind of brings on to channels. And a lot of kind of people have tried to use channels as a different way of doing Rx. It just doesn't work. So before I make the caveat that channels is super experimental, so even though Coroutines themselves, the library is going 1.0 soon, channels is still staying experimental. So just a bit of a thing to say there. And yeah, they are not replacement for RxJava publishers. They just don't have the same functionality. They do describe an asynchronous stream of things. Channels call these things elements, Rx calls them items, whatever, it's just semantics. But the fundamental difference is that channels only support hot streams, which for most of the time isn't what mobile apps are going to be doing. It's going to be cold streams usually. So let's build an example. We have an example which one side of our application, I don't know, some process somewhere, is going to load a series of images, and then on the other side, we are going to do some processing. It's the example we said earlier, but I'm going to try and insert a channel in there. The glue in between those two sides is going to be a channel, basically. So let's go for the example. Right. So we're going to create a channel of bitmaps in this example. And then we're going to have our first coroutine. And that is going to go through a list of files, which has magically appeared here. And in that, we're going to load a bitmap, and we're going to send it to the channel. So it's pretty simple. It's channels, for all intents and purposes, if you look at the API, is kind of like a queue. And that's kind of how I mentally think about it. It's a queue which works across coroutines. And then once we've finished processing our files and they've all been sent to the channel, we're going to close it. And that tells the receiving side of the channel that it's all finished and it can stop its processing. And then we go to the other side, the second side, where we're going to do that processing. Here it's in the same file, but it could be anywhere else in your app. We're going to call a method called consumeEach on that channel. And that's a special extension function, which itself will open a subscription, and then it will just sit there waiting for items to be sent to it. And then when the channel's closed, it will just basically exit. So that's a pretty simple example of using channels, really. So we go back to some of the theory behind it. So broadcast channels are kind of similar to subjects. They do kind of the same thing. And conflated broadcast channel, which is, I don't know where the conflated comes from, is kind of equal to behavior subject. So it keeps one item, and that's kind of like, it's the item for that channel, that subject. Some differences that I found when I've been doing this kind of stuff is that channels support null values, whereas RxJava doesn't. If you try and send RxJava a null value, it will crash. Now, not that you really should be sending null values to a channel, but I don't know, it does. And as I said earlier, channels only support hot streams. So one of the things that always comes up with channels is operators, and a distinct lack of them on channels. In fact, channels only has 73 built in, and most of them are kind of collection-y type, it's like map or folder or whatever it will be. RxJava has a lot more, 230 when I was looking. Now, of course, not all of these will actually be applicable in Kotlin, because some of them are trying to do like function 1, function 2, function 3, just because they don't have default parameter values. But you can imagine that RxJava has a lot of history there. It's a lot of stuff built up, which is actually good and bad. It's good because the functionality is there. It's bad because someone new coming into RxJava, the mental model of learning it all is just insane. And so yeah. One thing I have found is that writing your own operators is easier to write in coroutines. So here's a small example, which is actually re-implementing map, and it's pretty simple, really. If you're trying to do that in RxJava, you'd have to write like 4 classes. So yeah. And so the final bit of this talk is about actually trying to apply these two things, like channels and coroutines to Android APIs and to make your lives easier. So the 2 examples I have are all about location. The first is getting the last known location for a device. which is pretty much a one-shot callback. So we're going to use the Fuse Location Provider client, which I'd recommend most people use, because it gives you like a single API entry into GPS, mobile networks, Bluetooth, blah, blah, blah. It stops you having to create all these different providers. It's in Google Play Services, and because it's in Google Play Services, it uses a task class, which is kind of their internal version of a feature. So to actually use that in sort of standard world, you sort of do play services client dot get last location dot on a complete listener, and then you get the location back as a callback. So what we actually want to do here is kind of convert that callback API into a suspended function, basically. So the Coroutines library gives you a lot of utility methods to do exactly this. One of them is called suspend coroutine. And what it will do, it will run the lambda you provide, and then immediately suspend. And then you are given a continuation to later resume. We'll see how that actually works, but basically it's exactly what we want to convert a callback API into a suspended function. There's a special version called Cancellable Coroutine, which just adds cancellation to the mix as well. And it allows the caller to actually cancel your call. Whatever. So let's build our function. So we're going to do, it's going to be called get last location, and it's going to return a location. That's the important thing. It's not return the callback or a future or whatever it is, it's actually return the individual location. So we're going to use that suspend cancelable coroutine builder I spoke about earlier, and we're given that continuation as the parameter. Here we're going to call our Play Services API, add an onComplete listener, and the way you actually call back to the coroutine, so we're converting these APIs, is via that continuation. You call continuation.resume with the result, and that's how it populates all the way back to the actual caller. So you can imagine that this actually is applicable to a lot of APIs in the Android sort of framework or libraries or whatever it is, and you can easily convert these into sort of coroutines. To go even further, the task class in Play Services is actually has a success and a not successful state as well. So if there is an exception that happened, whatever reason, you can also populate that back up so that the caller will receive that exception. And that's done with another method on the continuation called resume with exception. I'm probably going to skip this bit because I don't think we have time. But you can find the slides online. So it's all about, instead of just doing a one-shot callback to get last location, you can observe locations. Look for the code, it's pretty simple, but it uses a channel internally. So I think that is about it, so I think we only have 2 minutes left. So what's next? So I'd say the two things I'd probably look at if you're interested in this. We have a code lab, which was published about 2 weeks ago, which is pretty good. It goes through some of the basics of what I've just spoke about, and it gets you kind of trying to use it. So you can find the link there. And also the manual, the docs are really good. They're very use case based, so they're all about, I want to do X, here's how you do it. And so the docs are actually really good. So I'd make sure you go and read them. And that is me. Thank you very much.